Language models are transforming the field of natural language processing. This presentation explores the fascinating phenomenon of emergent abilities in these models where unexpected capabilities arise as they scale up. We will delve into what causes these abilities and why they are so unpredictable. Language models have revolutionized natural language processing, leading to significant advancements in various applications. Increasing the size of these models through more training and parameters generally boosts their performance. While scaling laws can often predict these improvements, some tasks exhibit unpredictable behavior as models grow. Emergence refers to the qualitative changes that arise from quantitative shifts within a system. This concept is relevant across various fields including physics, biology, and computer science. In the context of language models, we examine how changes in model scale such as the number of parameters lead to unexpected behavioral changes. An emergent ability is defined as a capability that is not present in smaller models but appears in larger models. These abilities cannot be predicted by simply extrapolating from the performance of smaller models. Instead, scaling curves often show a sudden jump in performance after a critical scale threshold is reached, resembling a phase transition. Several factors influence the scaling of language models, including computation, the number of model parameters, and the size of the training dataset. While training compute measured in flops is often used as the primary metric, model parameters also play a crucial role. Emergence is influenced by a combination of these correlated variables. The scale at which an ability emerges is not fixed but depends on several factors. For instance, models trained on higher quality data may exhibit emergence with less computation or fewer parameters. It's important to remember that today's language models are likely not trained optimally, and this presentation focuses on showcasing examples of emergent behavior rather than defining precise emergence scales. Few-shot prompting is a key paradigm for observing emergent abilities in large language models like GPT-3. This involves providing the model with a task prompt and generating a response without additional training. The ability to perform a task via few-shot prompting is considered emergent when performance jumps from near random to significant levels at a certain scale. Figure 2 showcases 8 emergent abilities observed across 5 language model families. Specifically, figures 2a through D highlight few-shot prompted tasks from Big Bench, including arithmetic, IPA, transliteration, word unscrambling, and Persian question answering. Models like GPT-3 and Lambda exhibit a clear performance jump at specific training flops, demonstrating emergence. Additional examples of emergent abilities can be seen in tasks like TruthfulQA, grounded conceptual mappings, and the massive multitask language understanding MMLU benchmark. Smaller Gopher models show random performance on TruthfulQA until scaled up significantly. Similarly, grounded conceptual mappings see a performance jump only with the largest GPT-3 model, and MMLU performance surpasses random guessing only after sufficient scaling. The word in context or weak benchmark demonstrates the impact of extreme scaling. GPT-3 and Chinchilla, even at their largest sizes, fail to achieve above-random performance on this semantic understanding task. However, above-random performance emerges when PaLM is scaled to 2.5 times 10 to the power of 24 flops, which corresponds to 540 billion parameters. Beyond few-shot learning, recent research has explored prompting and fine-tuning strategies to enhance language model abilities. A technique that shows no improvement until applied to a large enough scale is also considered an emergent ability. Chain-of-thought prompting, which enables multi-step reasoning, only surpasses standard prompting when scaled to 10 to the power of 23 training flops. Instruction following, where models perform tasks by reading instructions, shows that fine-tuning can actually hurt performance for smaller models, only improving with scale. Similarly, using a scratchpad for intermediate computations only helps larger models. Even model calibration techniques such as the true-false method show emergent benefits at the largest scales. It's important to note that these emergent abilities can also bring emergent risks. Currently, there are few definitive explanations for why emergent abilities arise. For multi-step reasoning, it's hypothesized that model depth needs to be proportional to the number of steps. For tasks requiring world knowledge, better memorization through more parameters and training may be key. Further research is needed to fully understand what enables scale to unlock these emergent abilities. Emergent abilities have broad implications, including potential risks related to truthfulness bias and toxicity. These advancements are also driving sociological changes in how the community views and uses language models. Future work should focus on training more capable models, improving task performance, and developing better architectures and training procedures. Ultimately, understanding emergence is crucial for predicting and harnessing the